Okay, so I'd like to start by again thanking the organizers, John and Hideo, for inviting me to what's so far for me at least been a very educational conference. And in this talk I'm going to describe some work I've been involved with in the large-scale integrated photonics group at HP Labs in California on trying to realize large-scale nonlinear photonic circuits. So here's an outline of my talk. I'll first describe a semi-classical approach that we've used to model quantum noise in highly nonlinear optical circuits. I'll then show some numerical simulation results on these circuits, and then finally I'll describe our experimental approach to hopefully make this a reality, at least in a laboratory type setting. So just a brief motivation for this work. So all optical computing actually was a very intensive research topic decades ago, and perhaps it didn't realize quite what people were hoping for in terms of revolutionizing computing at the time. But there's been a lot of renewed interest in this topic lately because of our improved ability to make very small photonic structures that can confine light to very small spaces, increase effective nonlinearities. So here's pictures of a couple of structures that we've made. This is micro-ring resonator and amorphous silicon platform, and this is a photonic crystal and gallium arsenide. It's very unlikely that these kinds of structures would replace electronic computing methods such as CMOS for general purpose computing. However, we think there are some very interesting possible applications for communications. So one of our interests is to study the effects of quantum noise in all optical classical logic. So unlike most of the talks here, we're actually not trying to make a quantum information processing device, but we're interested in how quantum effects affect the behavior if we operate at what to us are ultra low energies, and by this I mean tens to thousands of photons. So for, I think most people here, that's ultra large energies. But if you limit yourself to devices that are relatively easy to fabricate and inexpensive, then it's, and furthermore, it would be nice for it to work at room temperature, then it's actually pretty difficult to get down to tens to thousands of photons. So the state of the art right now is carrier-based nonlinear devices from Natomi's group at NTT, and they're down to on the order of 10,000 photons at room temperature. Of course, if you go to low temperature quantum dots, you can get closer to tens or even single photon switching. But the nonlinearities that we're interested in are bulk nonlinearities, such as the Kerr nonlinearity. This is what I'm going to mostly talk about with the theoretical modeling. But carrier-based nonlinearities and thermal nonlinearity is the slowest one, but perhaps the easiest to use because it tends to dominate on large time scales. So the first problem, if we want to simulate quantum noise, of course, is that if we used a brute force approach, we need to have something like 100 Fock states for each resonator, and we want to simulate something like 100 resonators coupled to each other. So we need to simplify the problem somehow. And so the approach that we're using is a semi-classical approach, and the equations describing a single resonator that we're using are of course nothing new, and there are a lot of papers on this kind of approach, but my favorite is this paper by Carter from 1995. And our main contribution, and this work is in collaboration with Nicholas and Ryan Hamerly and Hideo's group, is to use this method to simulate very large, complicated circuits. But just a very brief introduction to this. So we'll be using stochastic equations where these complex numbers alpha correspond to random samplings of the Wigner distribution of the cavity modes. And so this can be written in terms of the density matrix with this transform. And our first step in deriving this is to derive Fokker-Planck equation for the time evolution of the Wigner function, starting from the time evolution of the density matrix. And then we use these relations to convert photon creation and annihilation operators that we get from these terms inside the Wigner transform into cavity field or field derivative terms outside of the Wigner function. And so, for example, if we want to study a resonator coupled to several waveguides, there's more than one approach we can use, but one approach is to start with a full Hamiltonian, including both the nonlinear cavity, the waveguide modes. So here J is the index of the waveguide, and omega is different modes in the waveguide. And then these are the coupling between the resonator and the waveguide. In this case, we don't have any dissipation terms. So then the Fokker-Planck equation we get for this multi-mode Wigner function is the one shown here using the method I showed on the previous slide. And in this equation, the first derivative terms, if we want to connect this to a stochastic differential equation, the first derivative terms correspond to drift of the field variable. The second derivative terms, if we had them, would correspond to diffusion. But for this particular nonlinearity, we actually don't get second derivative terms here. And then the third derivative terms, unfortunately, don't have a nice correspondence to a stochastic differential equation. And so we end up just dropping them. And our rationale for doing that is, if we look here, if we're interested mainly in the large photon number limit, then these first derivative terms will be a factor of alpha squared larger than these third derivative terms, assuming that the derivatives are of order 1 or smaller. The consequences of doing this are discussed quite a bit in this Carter paper here, but obviously it's going to limit the regime of where this can be accurate. So then the corresponding differential equations we get for the field variables are these here. And so the noise enters through, because these field variables correspond to random samplings of the Wigner distribution, the noise enters through the initial conditions of these fields. But if we assume constant coupling coefficient as an input-output formalism and then take the continuum limit, then we end up with these final equations. So this I think looks quite familiar. So we have time derivative of field, includes internal dynamics, detuning, energy decay of the cavity, and the nonlinearity. So this is a nonlinear frequency shift of the cavity. Then we have a time-dependent input field, and then the output field is equal to reflected input field plus the light that's escaping out of the cavity. And if the input is a coherent state, then this input field is delta correlated with coefficient of fourth for each of the real and imaginary parts of the input. The alternative way to derive this would be to start with the Hamiltonian for the resonator only and to include collapse operators for the interaction with the multiple waveguides, and we'd get the same answer. And this is actually the iteration that's shown in our paper. So then the question is, how well does this capture the kind of behavior that we're actually trying to study? And so here we're looking at a single bistable cavity, and we make this bistable by, if we have a positive Kerr coefficient, then we detune on the negative side from the cavity resonance. And classically, the reason this is bistable is that if we start with very weak drive, so this is plotting the average photon number as a function of the drive amplitude. Initially, because we're off resonance, very little light couples into the cavity. But eventually, if we keep increasing the drive, enough light couples in that it starts to shift the cavity into resonance with the drive laser. And eventually, there's a runaway effect where, as the cavity gets shifted towards the laser, more and more light couples in, and it jumps up to a higher state. Then if we lower the drive amplitude, the light that's already in the cavity will keep it in the upper state until we go below some minimum drive needed to maintain that, and then it collapses back down to the lower state. So classically, that's what happens, but if the switching happens at very low photon numbers, then we expect actually to have spontaneous jumps between these upper and lower states. And this can be seen both in semi-classical simulations using the method I just described and in a full quantum simulation using quantum optics toolbox. So qualitatively it looks similar, but if you look at this carefully, the jump rates might be slightly different, and also the exact drive field we need to get equal upper and lower state populations can be different in the two cases. So looking at this more quantitatively, these plots on the left are showing a case where the nonlinearity is quite large so that this switching happens at very low photon numbers. This upper plot is again showing average photon number in the cavity as a function of drive amplitude. The green curve is the classical solution, which looks like a cubic function. This black and magenta curves are the full quantum simulation, and this blue curve is the semi-classical simulation. And so you see that here the agreement actually doesn't look that good. And here if we separately plot the upward and downward jump rates, so upward jump rates here are in red and downward jump rates are in blue, and the solid dots are for the full quantum calculation and the empty dots are for the semi-classical simulation. We see that the main discrepancy is in the upward jump rate. And maybe this is expected because the lower state here has on average less than 2 photons. So it's certainly outside of the regime where we can say we have a large photon number, which was important in the approximations that we made. But if we look at another case where the nonlinearity is weaker and the switching happens at larger photon numbers, then we see better agreement between the full quantum and semi-classical simulations. And the main difference, if we look at the individual rates, is a horizontal shift in the drive field needed to get the same rates by about 1%. We can also look at the time average Wigner function in the two methods. So this is full quantum and this is semi-classical. And we see very good agreement there with the condition that we have to set the drive input slightly different in the semi-classical case in order to get equal upper and lower state occupation for the same reason shown here. So that's a single resonator, but to use this for large circuits, we have to do a bit more work. And what we want to be able to do is to specify a circuit layout either as a net list, which means a list of all the components in the circuit and how they're connected together, or else through a graphical diagram. And so the problem then is basically that we're taking the equations that I just showed and we're setting the inputs of some elements equal to the outputs of other elements when they're internally connected. But in other cases, we have inputs coming from outside of the circuit and outputs going outside of the circuit. So I'm not going to go into great detail on how we do it, but in our paper we describe an algebraic method for eliminating these internal connections and end up with a set of coupled stochastic equations for only the cavity fields, so this alpha vector in terms of the external inputs, this beta in. And so the problem is to find these matrices, A is cavity to cavity coupling matrix, B is external input to cavity. And then we also want to know the outputs of the circuit. So there are two more matrices describing how the inputs couple directly to the outputs, that's this D matrix, and then how the cavities couple to the outputs. So our paper describes an algebraic approach to doing this. Another approach that you can use is to start with a given cavity input and then propagate backwards through the circuit all the way until you reach an external input. And in cases where you have beam splitters, you'll split into multiple paths, so you keep track of all these paths. And each time you get to a new component, you add some contribution to your matrices until all the paths have terminated. And that method works well if you don't have loops in the circuit, but if you do have loops, then you end up having to do it iteratively. So then I would say that the algebraic approach is more efficient. So that's the basic method, and I'm going to describe some actual circuits that we've simulated. And the first one is this AND gate, which is taken from one of Hideo's recent papers. The only difference is that we've added some scattering loss to this cavity of about 20% of the total loss, because that's roughly what can be done experimentally. And so in this circuit, we have two inputs. They add, if they're both on, they add constructively at this beam splitter. Then they couple to this cavity. And if we plot the, again, average photon number in the cavity as a function of input amplitude, we're detuned from the cavity by about one line width in order to get this threshold-like response. And the parameters are set so that only if both inputs are on, we exceed this threshold. And then the cavity will be in a high state. Otherwise, it'll be either in a completely empty state or in a fairly low photon number state. And then we also interfere the two cavity outputs with each other in order to clean up the output somewhat in the case of the cavity being in the logical low state. And this is just simulating this one gate by itself, and we're using kind of the most unfriendly possible input. So we're using triangle waves on the two inputs with a fast period and a fast period and a slow period in order to just test for signal restoration. And we can see this in how, although in the high state when both inputs are on, we do see some variation in the output level. It's less than the variation in these triangle waves. And this is a very similar circuit. It's a fan-out circuit where we've replaced, it's like the AND gate, but we replaced one of the inputs with a CW coherent signal, and it's 180 degrees out of phase from the input, so the effect is to have this cavity only turn on when the input is off. So the drive by itself is enough to exceed this threshold, but if our input is on, then it moves the summed drive to below this threshold. The output of this is large enough that we can split it into two signals with similar amplitude as the input. And then the last circuit I'll show for now is this latch, also from Hideo's paper. And this now has two resonators, and they're set up so that if just one input is on, it will drive the corresponding resonator to its on state through a combination of the input amplitude plus a CW drive. But if both inputs are on, the circuit is set up to have a destructive interference from the output of one resonator to the input of the other. And so it's not possible for both resonators to be on if you use the normal drive levels here. And so the result is that it will remember its previous state. So whichever cavity was on before you turn both of them on will be the one that stays on. So this is a basic building block for memory in the circuit. So with just these three circuits, this isn't the most efficient way to build larger circuits, but it's enough if we want to just try to demonstrate a large circuit. So we can build some textbook kinds of circuits out of this. And this here shows a D-type flip-flop, which includes two of these latches. The first latch is set up so that with these fan-outs and AND gates, such that if we have a clock signal and a data signal, if the clock is high, the data signal gets loaded into this master flip-flop. And then when the clock goes low, the signal from this master flip-flop gets transferred to this so-called slave flip-flop. And then using this type of circuit, we can build something larger like this shows just an example of a 4-bit counter, which consists just of 4 of these D-type flip-flops, and in each case, we invert the output and feed it back to its input. So this is a toggling configuration. So for each clock cycle, this flip-flop will go to the opposite state, so it alternates between 1 and 0. But then this output also uses the clock for the next one. And so we just end up with a series of outputs that each one has half the frequency of the previous one. And for the parameters used here, the circuit works. We don't see any errors. But what we're interested in is seeing how low of powers or how strong of nonlinearities we can go to before we start seeing errors. And so this circuit is the first example of a fairly large circuit. It includes 88 cavities, which actually is more than you need to do this. It's because we're starting with fairly inefficient components. But this is a problem that we definitely have to use some approximation to have any hope of being able to simulate it at all. So now if we increase the nonlinearity so that the circuit operates at weaker drives, then we see it mostly works, but if you look carefully, you'll see some errors. So we're starting to see spontaneous jumps. And this is showing the simulated jump rates as a function of the design input level. And these red dots are for the entire counter circuit. And these blue dots are for just a single latch, so that's a 2-cavity circuit. And the first thing we notice is that the error rate for the larger circuit is about 8 times higher than for the latch. And since this counter circuit contains 8 latches, this suggests that most of the errors are happening actually due to jumps between the bistable states of the latch circuits. With this kind of result, we can also extrapolate to how weak of a nonlinearity or how large of a number of photons in the cavity we would need in order to get to what people would consider a computationally acceptable error rate, which is something like 10 to the minus 18 error probability per operation. So of course we can't simulate directly that kind of error rate, but if we just extend this curve, we estimate that we would need something like 180 photons in the cavity on state to reach that kind of level. And of course, that's just to avoid purely quantum errors. There are other kinds of errors that could happen, but that sets maybe a lower limit on the photon number that would be needed for switching. And then lastly, it's interesting also to look at the Wigner functions of elements of the circuit, either early in the circuit. So we're looking at cavities that are part of latches. This is near the beginning of the circuit, and this is near the end of the circuit. This is for the circuit designed to work at higher powers, and this is the circuit working at lower powers. And in both cases, we see that there's not really much change in the noise around the different possible states of this latch cavity. So this is showing that the quantum noise is not snowballing through the circuit. The main effect is to occasionally produce errors, which, if the error rate is low, will approximately add linearly through the circuit. So with that, now I'd like to talk about how we hope to actually realize this kind of complicated optical logic experimentally. And to start with, we have to look at single devices and their switching behavior. And here we're looking at a single amorphous silicon ring resonator coupled to a waveguide, and then these structures at the end are grating couplers that are used to probe this device. So in this case, the experiment is done using fiber probes to launch light in through this waveguide. It interacts with the cavity, and then it comes out this grating coupler. And the data here are showing a pump probe type experiment. This is work by my colleague Jason Pelk. And the x-axis here is a pump probe delay, and then the y-axis is the frequency of the probe. And so this is showing that when the pump comes in for a short time, the cavity resonance shifts in frequency. And if you plot this over a longer time scale, you see that in the single device, you can actually see all three of the main nonlinearities that you find in bulk semiconductors. The initial spike you see here is due to the Kerr effect, which is very fast. And the time scale here is limited actually by the cavity lifetime to on the order of 10 picoseconds. Then somewhat longer time scale, we have the carrier-based shift. This is so-called free carrier plasma dispersion effect. And this is a blue shift with a time scale of on the order of hundreds of picoseconds. And then finally, the slowest time constant here is for thermal relaxation, which is on the order of 10 nanoseconds. We're also trying to do this in 3.5 materials to try to get to much lower switching energies. And this is an example of a measurement on a photonic crystal cavity in gallium arsenide. So this is, again, showing a cavity shift as a function of time following a pump pulse. So in this case, the switching energy is quite a bit larger than the current record in the field, which is actually sub-femtojoule. So we're trying to still figure out why, but the hope is that with these 3.5 structures, we can get down to low enough carrier-based switching energies that we can overcome the thermal effects and be able to do CW bistability. But as I said before, the easiest nonlinearity to use is actually the thermal nonlinearity. And if we want to just test our ability to control a large circuit, which is quite a non-trivial task, if all the elements are actually talking to each other, then the easiest nonlinearity to use is the thermal nonlinearity. And this here is showing bistable switching, again in the amorphous silicon rings. This is plotting the transmitted power through a waveguide that's coupled to a ring resonator as a function of the input power. And so initially, as we increase the drive power, the output grows linearly, but at some point we cross a switching threshold and suddenly the transmitted power goes down. So in this case, since we're probing transmission, when the cavity goes to its high state, our measured signal actually goes down. And then we can keep increasing the input power and the output grows again. But then if we go back down, we have a hysteresis. So this is now below the initial switching threshold, but the cavity stays in its high state. So the transmission is low because the cavity is nearly on resonance with the light going through the waveguide. And then eventually, when we cross a lower level, the cavity switches back to its lower state. And so we can pulse the state of the system as shown here. So this is input signal we have upward pulses and downward pulses, and then this level here is to maintain in the bistable state, and then the response is shown here. So again, when the output is low, it means the cavity is in its high photon number state. So when we send in an up pulse, the cavity stays in its higher state, and when we send a low pulse, the cavity stays in its lower state. So we would like then to use this kind of behavior as a building block to make the kind of circuit that I was showing. But I should mention that in this field, there's a fair amount of skepticism about whether this is really feasible to realize complicated computing with this kind of component. So these are some criteria that were published in a recent review paper by David Miller, who's well known in this field of optical computing. And the first three criteria he listed, cascadability, fan-out, and logic level restoration. As I showed before, we can meet these requirements. But this fourth one, input-output isolation, we're not sure about still. And these next two, we're definitely trying to make the circuit work without meeting these criteria. So the first one is absence of critical biasing. While our devices do have to be biased fairly in a fairly well-controlled manner to work. And then the second one, logic level independent of loss. We're certainly dependent on loss, but we're hoping to have the loss be low enough that we can tolerate it. And he says specifically that coherent interference is mostly a nuisance in logic systems. And so we're hoping that this is an overly pessimistic statement and that we can actually use coherence for computing. But we'll see. If he ends up being right, there are other things we can do with this kind of circuit besides digital logic. Digital logic is kind of the most unnatural thing to try to force light to do. But that's what we're trying to do first. So the current state of the art in terms of making circuits with many bistable devices is this work from the Natomi group at NTT. And this is a picture from the recent paper showing a device with 128 separate bistable photonic crystal resonators. And they're designed to each have a different resonance frequency, and they can all be controllably switched into their upper and lower bistable state. However, they don't talk to each other, so this doesn't quite do what we want to be able to do. And so if one of these didn't work, all the other devices would still work. But we're trying to make a circuit where every component depends on every other component working. And so the first question then is the kind of circuit that I showed, how sensitive is it to variations in the fabrication parameters? And so these are simulations as we randomly vary parameters like the phase shift that light gets when it goes from one component to the next, or if we have variation in the transmission of beam splitters. So here we're looking at standard deviation of the relative variation of the transmission of a beam splitter. And we find that typically, so the blue curves here are for the entire counter circuit to work, and we find that generally these parameters have to be controlled to within around 5 to 10% of their nominal value. So that's quite difficult to do through fabrication alone. At least with our fabrication abilities, we don't think that this is possible. So to really be able to do this, we need a circuit with some kind of tunability. So this is another way to look at the kinds of circuits that we're trying to build. It's really a complicated nonlinear optical interferometer where we have a small number of signal inputs and a much larger number of constant inputs that are supplying power to the circuit. And then we have also some clock inputs that are basically square waves. And then we have a small number of signal outputs that we're originally interested in, but then we have a large number of additional outputs that we're just throwing away. But what we need to do is to actually use these other outputs for diagnostics of how the circuit is working, and then based on that to apply corrections to all these inputs in order to tune the circuit into working. And to be able to do this, it helps also to make circuits that are tunable. And our current approach to these circuits is to, first of all, avoid unnecessary on-chip interferometric loops, so to only have loops when they're logically necessary. And then for each resonator to have a separate external CW signal that's being inserted right before it so that it can be individually tuned to close to its switching threshold. And so this is an example of a much simpler latch type circuit. So this is half of the D-type flip-flop. It includes a first stage which is an AND gate between the input and the clock plus the CW bias. And then a second stage where this cavity is farther detuned so that it's bistable. And there's another clock injected here. And this is set up so that if the clock is low, then this is mainly driven by the second CW signal, and this cavity is held in its bistable regime, so it remembers its previous state. But if the clock is high, if the signal is high, then output of this AND gate will force this second cavity high. If this signal is low, then the second clock signal will destructively interfere with this drive to force the cavity low. And then we have enough intensity coming out of the second cavity that we also can split into multiple signals. And then to be able to realize this, at least in the lab, we also need to be able to control hundreds of external inputs, and we need to control both the amplitude and phase. So in our initial attempts, we're going to use spatial light modulators in order to be able to control all these inputs. So we'll have phase and amplitude spatial light modulators, image this onto a set of input grading couplers on the chip, and then to diagnose how the circuit is working, then we can image from above with a camera. And this movie here shows that we can easily see the vertical scatter out of the cavities when we switch. This is just switching a single device to its upper and lower bistable states. And then here's an example of a circuit that we're more interested in than the counter. The counter was just to sort of to test some general large circuit, but this is a circuit that could have some interesting applications for communication. It's still sort of a toy circuit, but this is an all-optical packet switch kind of circuit. So it includes a 7-bit shift register and then an AND gate which looks for a sequence of 3 ones which signify the start of a new packet. So the 3 ones are a keyword. If they're found, then address bits that follow the keyword are loaded into two address registers, which then control a 1 to 4 switch, so that the output the data is routed to one of 4 outputs. And this will keep happening until another keyword is detected, and then a new address will be loaded. So this is a circuit that has about 70 cavities. And so then the question is, if we start out with completely random phases in all of the propagation distances between components, which is likely to be the case with fabrication because these phases are highly dependent on not only the length of the waveguides, but on the other dimensions. So the width of the waveguide, for example, which can vary from fabrication run to run. And so this is just showing a time lapse of a very straightforward algorithm that you could use to try to tune this circuit into working. And with this kind of system, it's not feasible to just start with random initial values and then just kind of search for the solution, because the solution space, I think, is way too small. So this algorithm is using a rational kind of approach to how the circuit is supposed to work. It's certainly not an optimal solution, but at least this shows that the circuit is solvable. But I think a really interesting problem would be how to do this more optimally. But what this is doing is it's basically starting with the first cavity where the inputs are all known. Then it's varying both an on-chip, well, in the first cavity you don't need to use on-chip phase tuner, but you start varying the off-chip amplitudes and phases to get this first cavity working. Then the inputs are known to the next cavity and you keep propagating. And then you get to some more interesting structures with multiple on-chip inputs like this AND gate. Now you have on-chip interferometric loops, so you have to vary on-chip phase tuners as well. But it's still straightforward until you get to these address registers where you have actually a loop. And then you're forced to solve a component without all its inputs being known. So you have to solve a circuit with partially known inputs and then keep propagating and then close the loop and then finish solving that component. And then you can solve the rest of the circuit. And then this is just showing how this algorithm works on a single cavity. So it's working on this AND cavity. It's going through a sequence where it's first varying an on-chip phase tuner, comparing the behavior with that expected from the ideal designed circuit. Then it's varying the external input amplitudes and phases. And then the final tuned circuit is how it operates is shown here. So when you see 3 ones go by, that's a keyword, and then immediately after that, an address is loaded into these address registers, and then this changes which output is being, the output is being sent to. So with that, I'm going to summarize. And so what I've shown is, first of all, a semi-classical simulation approach that we've used to simulate large-scale circuits. I showed an example of a fairly large circuit with about 80 cavities that, from our simulations, we estimate needs, if we could make the nonlinearity anything we want, then we would need about 180 photons on average to avoid errors in the circuit. I showed an approach for how we hope to be able to tune nonlinear circuits that have realistic fabrication variation. And I showed some initial experimental results on switching in single devices. And in the future, first of all, I should say that Nicholas and Ryan have added this kind of semi-classical capability to their QHDL model. So this is a very nice setup for being able to do either full quantum or semi-classical simulation of the same circuit on the same platform. We're interested in other kinds of nonlinearities besides the Kerr nonlinearity. This work is mainly being done in Hideo's group, but I expect this to be very useful for simulating the systems that we're going to be working with experimentally in the end. And then, as I said, we're hoping to actually realize this at least at a laboratory demonstration type level for fairly large circuits with on the order of 100 components. So with that, I'd just like to acknowledge the people who contributed to this work. So in our group, Jason Pelk and Ranjoy Bose are the main people working on this project. Kelly Rivoire also contributed early on. And Cheng Li is helping us now with electronics. And then the semi-classical work was in collaboration with Nicholas and Ryan and Hideo's group. So with that, thank you for listening, and I'll look forward to any questions.
I'm not sure if I understood it, but did you model the thermal nonlinearity, or was that just experimental data?
So I'm not sure which result you mean.
Where you had the switching based on the thermal nonlinearity?
This one here, this is experimental.
Okay. So would you not model this in the same way with the Kerr terms and the Hamiltonian, or is it clear that that's the right description?
So the behavior of a thermal nonlinearity is quite similar to the Kerr nonlinearity, except that the time constant is controlled by the semiconductor instead of the light in the cavity. So we can actually simulate this correctly using a model for the thermal dynamics in the system rather than using the Kerr Hamiltonian. So the results are fairly similar but not exactly the same.
So summer nonlinearity should be a triangle. Why is so? Should be a triangle, is it right? Why is so strange shape for this?
So you mean this, or?
Yeah.
Yeah, that's a very good question. So on this downward sweep, there's this kink here, and this is very recent data, and I actually had the same question when I saw this, and I'm not sure yet what this is. So it could, just very speculatively, if this is real, it could have to do with being very close to a critical coupling condition where all the light gets blocked, but I'm actually not sure why this is happening. It's possible that the system is behaving in some non-ideal way.
Also a small comment. So for thermal nonlinearity, it's dissipation effect, not coherent. So it's maybe somewhat different from Kerr nonlinearity.
Yeah, it is different. So it's thermal nonlinearity means basically that we have light being absorbed in the cavity. It's being converted to heat, and that shifts the refractive index because of the thermal optic effect. And the time constant for that is much slower than the photon dynamics in the cavity for at least the quality factors we have. And yeah, you need to, if you want to treat quantum noise in that system, you need a very different model than the one that I showed.
Can you go back to the Miller slide?
Oh, I think I have to go this way. Okay.
So I guess number 4 and so number 4 you weren't sure that you could do, and number 6 you did think you could do. Is that?
Yeah, definitely our logic levels depend on loss, so this is something we're trying to violate.
So can you do like usually you get around that through differential signaling, and especially if your latches have an out and a logical not out, then that sets up very nicely for differential signaling to the next stage. In the microwave latch that I did, that was definitely the case, and that's sort of why I thought that I could, you know, if I wanted to do another experiment, I could have them cascaded after each other. If you look at some of the large-scale optical computing demonstrations that Miller and people at Bell Labs did, that it worked in the same way. And but I guess in the latches that you showed, there was just one logical out. There wasn't a not out as well. Is that correct?
Right, there's just a single output.
Okay. Is there a hidden not out through one of the other ports that you just weren't considering?
There are other outputs. They're kind of messy signals, but there is information in them that possibly could be used.
Okay. Well, at least in the way that I did it, there was very clear there was an out and a not out. And then for number 4, also looking at those optical computing papers, the way that they did input-output isolation is it was the computation was done in very discrete sort of columns of progressing, where this column of latches would output to this guy and then set all those states. And even if there was back reflection, they did computations in manners that they actually just erased whatever was back reflected on here and reset all those states to some 0 state. And then but then just sort of kept on going like that. So that's how they did it in those very large scale things for achieve number 4, and that might be possible here as well.
Okay.
So, well, I had a question about that. So, yeah, I mean, is that just this back reflection issue? And if it is, couldn't you have Faraday isolators to solve that, or does it mean something more general?
Yeah, in principle, you could use Faraday isolators. That is a fairly difficult component currently to make, but there has been at least research on demonstrating those. And yeah, just generally the thing I'm worried about, so you saw that we use a lot of ring resonators, and ideally you never have light coupling into the backwards mode, but sometimes we see fairly strong coupling, like if there's some strong scatter on the ring or otherwise there's splitting between the
Experimentally.
mode. Yeah, experimentally sometimes you see strong backscattering, so it's definitely something that could throw off the circuit if it happens.
Okay. So your models have input-output isolation. Is that correct?
Well, our models don't have any, they don't even include a counter-propagating mode in the waveguides.
Right.
And we have no
Yeah.
way to couple into them. Yeah, so
Yeah.
it's,
Okay,
So-
so that's a yeah. So when you say you don't know whether you can achieve that, you mean because of the experimental reality.
yeah, that's right.
Yeah. Okay. Final question.
So do you use kind of classical error correction at all in these kinds of setups? Can one use to like reduce the increase the threshold allowed in your devices?
I didn't quite catch the question. Do we use classical
Do people use classical error correction with optical logic?
classical error correction? So in the field of all optical computing, at least in terms of doing a complicated digital logic-based error correction, I don't think that people have made complicated enough circuits to be able to do that yet. So but I would say it's something that in principle you could do, but I don't know whether it would be better to actually do that or just to aim for lower error rates in the first place.